Okay, so for this linear regression guided practice, I'm going to go over these main points. So first, talk about a regression-driven EDA. I mean, of course, when you're doing your EDA, you should do the typical, like, what are you intrigued by with your data? Getting to know like the distribution of your data, but I'm going to focus specifically on EDA that is going to help you a lot with your modeling and help make sense of your modeling as well. Pretty much related to the assumptions. Then I'll talk a little bit about iterative modeling and what that looks like and how you can streamline that process as well. I have like a function that you can definitely take and adapt for your own projects. And then finally, I'm going to talk about model evaluation. There's a good bit here. I'm going to talk about metrics, why you want to keep track of more than just an R² value. Again, continuing with some of the post-modeling assumptions that you always want to check for, and then looking at coefficient analysis. So part of the rubric for phase 2 is you have to interpret at least 3 coefficients. And depending on how you go about your modeling process, that might look different. So I'll talk through those as well. Things that I'm not going to talk about. I'm not going to talk about data cleaning. That's kind of like a phase 1 thing. So null values, you know how to take care of. I'll talk about scaling though briefly. But any of like the simple data cleaning, getting rid of all of those like object columns, that I won't talk too much about. The data set that we're going to talk through today is the Lego data set, and that's actually the data set that is in the appendix section of phase 2. So if you haven't looked at it yet, I super recommend that just because that appendix section is pretty much a guided linear regression practice with this data set. So I've adapted some of that. I actually took some of the code from some of those labs. I'll explain some of it as well. That's a little bit more complicated. But yeah, let's just get into it. So first we have our CSV over here. By the way, if you like ever wanted to use a CSV without having to download it, you can actually get the raw file. Actually, since we're here, I can show you all real quickly. Let's just say that I have a CSV from here. This is just a random one that I have. If you have a CSV here, if you just go to raw, all you have to do is pull out this URL and you don't have to download the CSV. You can actually use it in your local notebooks as well. So that's like a neat trick. If you ever like, if something's not working on a Lumadesk, you need to work locally, you need data file, that's a quick way to do that.
Does that work offline too? So like say you're not connected to the internet afterwards.
That's a good question. That's a good question. I don't think so because it is pulling from the internet address. So it might, I don't think it'll work offline, but I've never been in a situation where I had to try it. I'm pretty sure it won't.
Like say you were on like a plane and you were working on it and all of a sudden like you don't have internet.
Yeah, I would say in that situation, I would, with internet, do this first, download the CSV, maybe do a 2 CSV through pandas. Easier, in my opinion, than like cloning an entire repo if you don't need it.
Perfect.
Cool. All right, so this is our data set. What we're trying to do is we're predicting the list price of a Lego set given some of its features. So I took one of the like, this is like a version of the data that has been somewhat cleaned already. It's in like, it's within the progression of that appendix section. So we have things like product ID, the age group, theme, list price, which is what we're trying to predict, reviews, star ratings, difficulty. So these are some of the features that we're going to use to predict price. So the whole point of a regression is we're trying to predict a continuous variable based on some other features. And these features can be either continuous or discrete. So as some really, really quick data cleaning, I'm doing some cleanup to get rid of any of the object variables. As you see here, our target, and this is what we're trying to predict, is currently, it has a $sign, so it's a string. So we're just cleaning that up. Other things we're doing, I'm filling in all the null values with median. And this is very, very arbitrary, just for this purpose. Very arbitrary data cleaning here, filling some null values with unknowns. Also, one thing that I'm doing here is when I create the dummy variables, which if right now dummy variables is not something that you've seen yet, that's okay. But one thing to note when you're doing your modeling, if your column names have weird symbols, so anything that isn't an underscore, it will actually throw an error on stats model. So make sure that you're getting rid of, I think in this example, some of them have like plus signs. Some of them have this like half symbol. They're like, I don't know, some of these symbols, and that'll actually throw off the model. So you want to change those. So replacing some of them with nothing, replacing some of them with like underscores. So that's just very, very basic formatting. All right, so to start with EDA, the main thing that we're going to focus on are the two assumptions that you can check for prior to modeling. And those are linearity assumption and the multiculinarity assumption. So although the words are pretty similar, they're actually quite different. Linearity, you're always checking for linearity between your target variable and each of the continuous features. So that means that, let's say we're trying to predict list price. We usually want our other continuous variables to be correlated with list price. So that's linearity. Multiculinarity, which can sound like kind of the opposite of what we were talking about before, but the multiculinarity assumption is that you don't want any of your X features you don't want any of your continuous X features to be correlated with each other. So you want correlation to exist between X and Y, but not within your X's. Reason for that being is if you have two X features that are correlated with each other, and you're trying to pick the target variable, it'll be kind of redundant to include both in your model because the relationship between feature A and the target and feature B with target would be pretty similar. So it's actually to prevent redundancy in your model. And we'll actually see in one of the regression outputs later, if you have multiculinarity, and you don't really know what kind of threshold to use, and I'll talk about that in a bit too, your model results might give you a hint on what to do with that. So we have a lot of features in our data set now. Actually, let me output our data. Where is our data hid? Actually, let me get the one that's cleaned already. All right, so I think it is called df. All right, df.hid. So this is after, hold on, I have to run these real quick. There we go. df.hid here. Okay, so these are all numerical right now. You see the column names don't have any weird symbols either. Cool. So to do this, we have a lot of 0 and 1 columns. Basically, for the linearity and multiculinarity assumption, you don't have to do that on your categorical variables, mainly because those numbers are all 0s and 1s anyways. Any of your graphs would just be like a bunch of like points at like 0 and 1. So that's actually not super relevant. So we don't have to do the model-driven ED on that. Of course, you're going to explore the relationship between the target variable and some of your dummy variable columns. You can do that as well. It's just a little bit less relevant to regression modeling. So this is why I'm just subsetting my continuous features. And lucky here, we only have 5, so it's going to be pretty simple. So for linearity check, I have this code over here, which feel free to take if you'd like and adapt to whatever your project is. I'm doing 2 things. So this code might look a little bit complicated, but here I did subplots. So 2 times 3 subplots. And let me actually like zoom out a little bit so we can see. In the very first one, I just want to take a look at the distribution of my target variable. So this is a list price variable. Now, there is another assumption for normality that we'll come to later. Is often misinterpreted. So some people think that, oh, my target variable has to be normally distributed. That's actually not the case. Your target variable can be distributed however it is. Normality will come later with the residuals of the model, which I'll talk about later as well. So first we're looking at the distribution. Okay, we can see that we have a lot of outliers in the high prices, but most of them are kind of between like $0 and $200. And I don't know too much about Legos, but that sounds right. All of these other plots, these are all reg plots. You can use a scatter plot as well and include a line. But the line is actually really helpful to see what the actual relationship between 2 variables are. So for each of these, I ran a loop. I have the X variables on the X axis and your target variable on the Y axis. So all of these, the Y variable is list price. So especially when you have a lot of rows in your data, and I believe this one has maybe about like 10,000 rows, I think. A scatter plot or having this line is really important because if I was to just look at this scatter plot, just look at one of these scatter plots, I would have actually assumed that, yeah, there is kind of a strong correlation here, right? So if I look at this, I mean, the points are just like very, very condensed. I would not have guessed that like maybe all my points are in this lower corner here that actually forces the actual line to be there. So the line actually is really helpful, can tell you a lot because you might mistakenly think that, or you might mistakenly interpret that as, oh yeah, it looks to be positively correlated. So the line is good for that reason. Seaborn's reg plot, super helpful for that. So that's why that's there. Cool. When looking at this, some interpretation and notes for modeling, I like to do this while doing the EDA as well. So first, interpretation, let's take a look at the list price. We talked about this a little bit ago. A lot of outliers on the higher end, possibly cull in an iteration of the model. Later, we'll get to some of the modeling results, and I will sort of I'll sort of show you like when you might want to consider dropping outliers. Some people like to cut out outliers just like from the start of modeling, but you do risk the chance of like removing data that you might not have had to get rid of. So I'll show you all when is a good time to get rid of outliers. Next, these first two features, this seems to have a pretty solid correlation with the target, piece count and number of reviews. So we'll take note of that. And also the rating variables have a weak negative correlation with the target. I mean, again, because we have this line here, we can see, all right, we have this weak negative correlation, maybe something to take note of for modeling as well. So some notes for modeling. One possibility, and actually this is something that you can consider, if you have a lot of outliers, and especially if it's in your target variable, log transforming actually does tend to help a lot, mainly because log transforming tends to make outliers that are very further away relatively closer. I'm not really going to talk too much about log transform today, but usually if you have target variable that looks like this, doing a log transform kind of squeezes your points to look a little bit more normal. Something else, culling outliers, again, might change the correlation between rating variables and target due to the high density of points in the 4 to 5 star 0 to 200 price range. So again, that's kind of like another note of like all of the points that are in here. It's just because our data is very concentrated in the 0 to 200 price range. So actually getting rid of a bunch of these points maybe will help the line move up, move down, make a little bit more sense. Cool. So this is the linearity assumption. Of course, you don't have to do it in subplots. Some people like to do it in loop output one by one. Any thoughts or questions about this? Cool. All right. So next, let's talk about multiculinarity. So I kind of have like a gripe with multiculinarity because in a lot of projects, I see people just output like a massive scatter matrix. And if anyone has tried to run a scatter matrix plot, it takes a very long time to run. And if you have more than, like I would say more than 7 to 8 variables, it becomes very hard to read. I personally prefer heat maps because it's color coded. I mean, if you're doing a scatter matrix, my advice is to just make sure that you're only plotting the relevant features, because if someone's running your notebook, it's going to take forever. Also, it becomes very hard to read after a certain number of features. But anyways, multiculinarity check. Basically, very simple code. We're just looking at the correlation between each of our X features. So from this, you can see that I don't have my list price anywhere because we don't need that for our multiculinarity check. And all we're looking out for here is what X features are highly correlated with each other. Some people like to get rid of multicollinear features at the start at this point. That's fine as well. I'm going to keep them in as we move into the modeling step, just so I can show you all what's another way you can see if there is redundancy in your model. So based on this pretty simple code, we have a heat map over here. When you have more features, it's easier to see with the colors, in my opinion, too. Quick interpretation, it looks like there is pretty strong multicollinearity between all of the rating features. Let me zoom in a little bit. So we have 3 kinds of ratings in this data set. So just regular star rating. I think this is like the player star rating, and I don't know I forget what Val star rating. It's basically a different rating thing. And there's high multicollinearity. And again, this threshold does differ data set per data set. And also does, if you think about it mathematically, it also depends on the distribution of your target variable, which is kind of hard to check for. So at this point, I usually just make notes of what's multicollinear. So here between all of the ratings, and notes for modeling, maybe drop 1 or 2 of the variables depending on results, and perhaps check on number of reviews during this modeling step, because number of reviews is like 0.55. It's like a moderate amount of multicollinearity. So here I would just take note of what are the ones that you might want to look at when you have your modeling results out. Any questions about this? All right. So these are the main 2 linear regression assumptions that you can check for before you start your modeling. And again, whether you decide to do anything about it at the offset at this point, or when you're doing your iterative modeling later, and that's actually the process that I'm going to do, it doesn't really matter as long as you're documenting why you're doing your processes. All right, so get into iterative modeling. There are a few different ways you can do modeling. I'm not sure if you all have gotten to that point yet, but there are two libraries that you can actually do linear regression with, stats models as well as scikit-learn. Today, I'm just going to talk through stats models, but scikit-learn, if you get to that, you can use that as well. Some pros and cons. Scikit-learn is a little bit faster, especially if you have a very large data set. Scikit-learn does work faster because if you want to get into the math of it, scikit-learn uses gradient descent to solve linear regression, while stats models actually uses linear algebra to solve linear regression. So scikit-learn is usually a little bit faster, but the only reason why you want to use stats models is stats models gives you more model summary info. So you have that whole table with all of your like P values, all the coefficients. Stats models gives you that. So usually stats models is good enough. So to start, I'm going to do a train test split. And train test split actually comes in at the very, very end of phase 2. And I believe is not, I would confirm with your instructor, but I believe is not a necessity for this project. If you're like still pretty confused about train test split, I don't think is a requirement, but please confirm with your instructor. But anyways, I'm doing a train test split basically so that I can test that my model can predict the list price of Legos that weren't in my training data. Basically, can it generalize to unseen data? That's the purpose of doing a train test split. Basically, what we're going to do is we're going to fit our model on our train set and just see how it performs on our test set. So to do that, a little bit of preparation. The target is list price. I'm just going to make a list of my columns and remove list price from that. Purpose of that is so that we can set up the formula for linear regression. So we have X calls. These are all of the X columns that we're going to be using, and we need this to set up stats models. So here we have this formula here, and basically, if you haven't gone to stats models yet, you just need to give it this string of the formula to set up linear regression for. For some background, that syntax seems kind of silly for Python because Python is supposed to be like very variable based. The fact that it's like one long string. This is actually from R syntax, from the language R. That's where this weird syntax comes from, with like the little like squiggly line and all the pluses. Anyways, when you're doing OLS, you have to give it the formula and your training data. We're going to fit that, and we get this linear regression output. So several things to take note of here. First, you have your R squared, and especially when you're doing your technical presentation, and even if you're non-technical presentation, I would mention your R squared of at least your final model. And the R squared is basically a measure of how well your model is fitting the data. There is like a formal definition, which is basically that, okay, an R squared of 0.867 is, let me see if I remember this off the top of my head, is that this model explains 86.7% of the variation in list price of Legos. So I would throw in the formal definition in there when you're, cleaning up your technical notebook and presenting it to whoever's doing your review. So R squared is something to take note of. Also, you have all of the variables that we input into our model. We have coefficients. And the main thing we want to look out for, two things, coefficients and P values. So coefficients basically tell you the gradient or the slope or the relationship between each of your features and your target. And then the P value tells you how significant that relationship is. So basically, when you get to your final model, just note that you do not want to have any P value above 0.05. Because if you have a P value that's like 0.456, for example, this is saying that there is around like a 45.6% chance that that relationship is just randomly occurring. So because of that, you do not want to have high P values in your final model, especially. So from here, that's pretty much what I would take note of when you're doing your iterative modeling. So in terms of making your code a little bit cleaner, feel free to adapt this function to your project if you want. But you're pretty much going to be running this process over and over again. the purpose of this project is to test a linear regression model on different variations of the same data, whether you're doing, a subset of columns, maybe you're scaling features, whether you are, I don't know, maybe you scale some, feature engineer some others. The whole point is you're just fitting the same model over and over again. So you don't want your code to be very repetitive. Because of that, you should write some sort of function. I would say phase 2 is like the first phase project where you can really start to incorporate functions. So I highly recommend it. By phase 3, you should be really incorporating some functions in your project. So phase 2, you can kind of use this as a practice, but if you feel like that's like a lot right now, it's really not necessary, but I do highly recommend. So feel free to adapt this. So here I've written this function that basically takes in a train set and a test set. There are many different ways you can go about this function. So however you think works best for your workflow, definitely adapt. And what we're doing here is we're pretty much just fitting the model, because my idea here is my train and test set might change. Maybe in some of the train sets, I want to test out how scaling works. Maybe I want to test out how log transforming works. So my train and test might change. So that's why I'm using these as the input arguments. So within here, I'm fitting my model with stats models. And in here, you see I'm returning model. This part is a little bit confusing, but I'm returning models just so I can get that summary table later. And I'll show you all how that works a bit. But one important thing that I think is like not emphasized enough is an Rmse. So Rmse is another metric that is different from R squared that is also really, in my opinion, very important to keep track of. And I'll tell you all why in a bit. So when I run this function, the way that I would use this, I would just type in model, give it train test. Because it returns the model object, I do dot summary to get the table. Because in order to get that table, I had to do model.summary. I had to do dot summary over here. If that doesn't make sense, feel free to let me know. But anyways, when I spit this out, here I have 2 print statements that print out the train Rmse and test Rmse. This, how you interpret this, is basically the average error in my predictions. So while this 0.867 tells me how well my model fits the data, these numbers will literally tell me, like, in dollar amounts, how off are my predictions on average. So it's a little bit more interpretable. Usually if you're presenting something to a non-technical audience, this number would make a lot more sense versus R squared, right? Because here you can say, yeah, we built this model and there's like an average of about like a $37 error. So this is a good number to keep track of. If you are doing a train test split, printing both the train and test Rmses as well is really useful to check for any sort of overfitting. And I don't know if y'all have gone to overfitting yet, but there is a chance that your model might learn too much from your training data, such that when it sees your testing data is like, your model is unable to generalize to that. And a sign of that is if your testing Rmse is a lot bigger than your train Rmse. So in this case, I would say, like, if we're looking at the price of Legos, and if we're like $2 off, that's not too bad. But there is a chance that, let's say my train Rmse goes down to like $5, which is great. Probably have a really high R squared as well. But if I have a test Rmse of like $200, then what's the point of this model, right? If it's unable to predict on Legos that I don't have in my data set, is it really useful? So also things to keep in mind. And this is why I think Rmse is a good number to keep track of while you're doing your modeling. All right, so here we have our first model. And as you can see, we have some pretty insignificant variables just straight off the bat. You can see that our rating variables, the ones that we thought were multicollinear, or they are multicollinear, so far they're all significant. I guess aside from star rating that has like a just above insignificance, so far so good. Like they are still pretty, especially compared to like some of these other variables that are like super insignificant. Like I guess having the theme of Blue's helicopter pursuit has very little impact on the price of the Lego. So there's this, there's like some that are pretty much like very, very random. Like any of these, I guess, DC Comics Lego sets have no impact. So as a first step, and if you go through the appendix and if you go through all of the lessons, there are many, many different things that you can do in your iterative modeling. I'm just going to go through one iteration today because I want to talk more about interpreting the model. But anyways, one thing that you can do is remove these insignificant variables. And this is code that I took from this specific lab that will literally see, okay, if there is a variable that is that has a p-value of above 0.05, just drop it. What's really neat and what makes this process much easier is this model.summary is actually a set of data frames. So the reason why you have the code that kind of looks like this, where you're taking like tables.1 pd.dataframe, is because it exists in data frame format. You can actually like do your analysis on the output tables that you see from SAS models. So from that, I'm not going to go over exactly what this code is doing, but from there, the idea here is we'll keep only the variables that are significant at this point. So here, what I'm doing is I'm creating a new train test set just so I can use it with my function again. And one thing to also that you might want to consider is what you're naming different iterations of your data set. Because I'm not doing too many iterations, I'm just calling it train 2 and test 2. Some people like to overwrite their train and test set. I personally don't like doing that, just in case I want to like rerun a previous model. Anyways, this syntax is a little bit weird, but I'm keeping the significant features and I'm keeping list price from my old train and test set. So this significant features list comes from the list of names that I created over here. Anyways, this new train test set has fewer features than what we had before, and we can take a look at that. I think before we had like 99 features, and train2.shape has 59 features. So we've lost, oh, I guess 58, because one of them is the target. So we've lost about 40 features. Cool. And because I have my function, I can do model train to test 2, grab my summary, and that is done. As you can see, every time you remove insignificant variables, there is a chance that other variables might become insignificant. So that's one thing to look out for. But anyways, it looks to be that, okay, I guess now we have this one that's 0.7, but this is kind of an iterative process. You can do that over and over again. Just keep culling the insignificant ones. Mm-hmm.
So, and I haven't gotten up to this material, but why does it change? Maybe that's too broad a question, but
that's okay.
Yeah. So we remove the things that are insignificant, and then we run it again. Like, why
would the p-values change?
Yeah, I guess.
Yeah. So these p-values are actually calculated not solely by looking at the correlation of, let's say, what was one insignificant one? Let's just talk about, let's see, what's an easy name to say? Okay, let's say something that was like an Australian Lego set has a very high p-value. This p-value is not solely calculated over the relationship of just Australia and the target variable. This p-value is kind of calculated based on the relationship of all the features put together with the target variable. So when you change the number of features that you're putting in, or you just change the features that you are putting in, the calculation just changes. So here we're considering 90 different variables at the same time, and relative to the other 90 variables, this one is fairly random in terms of the relationship with list price. But when we lower it down to 50 or 60 variables, that relative relationship changes.
Okay. So that's like behind the hood calculations that are going on. Gotcha.
Yeah, not something that we have to worry about directly.
Okay.
Yeah, but good instinct. Something else that is interesting to talk about, since we're talking about p-values changing, I guess now is a good time to talk about scaling. If you decide to standard scale your variables, you typically will not see a difference in the p-values of your variables when you're standard scaling them. Reason for that being is, let's just say I have a feature that looks like, I'm just going to draw a really janky graph over here. But let's say I have like a feature that looks like this, and it ranges from like 0 to like 90, for example. When I do a scalar on my data, it basically tries to recenter my data so that it's like roughly mean of 0 standard deviation of 1. But standard scaling, or something like a min-max scalar, actually doesn't change the shape of my curve. Standard scaling pretty much just like squishes things down and like shifts them across the axis. So because of that, the relationship with list price doesn't change. Your slope is going to change because the unit change in something and versus the other will be different because the scale of the number is different. But you shouldn't expect to see big changes in your p-values. However, this is different from log transform. So let's just say I have data that looks like this. If I log transform it, I'm going to attempt to draw this. Log transforming my variable has the effect of squeezing extreme values closer together. So by doing a log transform, you are actually changing the distribution of your data or the relative distance between data points. So if you want to see a change, or if you are doing your iterative modeling and you're like, okay, I want to change, or I want to see what the impact of changing the distribution of my data looks like, log transform actually tends to have a stronger impact versus just standard scaling. But there is a reason to standard scale, and I'll talk about that in a bit too.
Oh, I have a question. Yeah, so for standard scaling, we should go through and do that to all the features, I guess, or?
Yeah,
like,
I would say so. Yeah,
Okay.
when you're doing standard scalar, and the reason why you would standard scale is to pretty much compare all of your features on an equal playing field. So yeah, I would do it on all features.
Okay, including the dummy variables, I guess?
Yeah, including
okay.
dummy variables. Although it won't make a big difference because dummy variables will just have zeros or ones. When you standard scale that, it will just have like some random, just 2 unique values of different decimal values.
Okay.
Yeah.
Cool.
Awesome. Anything else? I know this is kind of like a tangent, but I think is worth talking about.
Oh, I actually.
Is the log? Sorry.
No, go ahead. Sorry.
I was just gonna say if the log scaling is what you do when you feel like outliers are affecting the results. Okay.
Yeah, log transforming actually can help achieve better linearity assumptions, like the one that we're checking at the start. If you're implementing log transform, a really good way to check to see if it's helpful or not is to actually go up and see if after you log transform, do these relationships look better or more linear?
And I guess with that log transform, we would go through each individual feature and apply that, or probably not all of them, or
you technically could do all of them. One of the downsides of doing log transform is it makes things harder to interpret. So because of that, I would only log transform if you feel like you have to.
Okay, cool.
All right, where was I? Okay, so we've done this second iteration. We've removed insignificant features. And okay, cool. So now we have this model. And as you can see, when you're doing your iterative modeling, I forget what the rubric says, but I think you want to have at least 3 or 4 like significant changes in your model. Keep track of your R-squared, keep track of what your Rmse is like. So it looks like here, did we do a little bit worse? Let me see. 34 and 36, and now we're at like 35 and 37, which is actually normal to not have your metrics always get better. By removing insignificant features, we actually end up having a more consistent model. So sometimes people will take a little bit worse of a metric just to make sure that their model is going to be reliable over time. And actually the other assumptions that I'm going to talk about right after this also relate to model consistency. Cool. Any questions before I talk about some more like assumption check stuff? Okay. Yeah. Sorry.
Okay. So I was watching like Greg D'Amico's one of his like end of the lesson videos, and he made a constant term. Is that necessary is that necessary all the time, or like maybe for the project?
Is it like the add constant thing?
Yes, yeah.
Yeah, so the add constant, it depends on how you are using stats models. So if you're using stats models with this syntax, with like the target plus predictors, you don't have to do the add constant.
Okay.
Yeah, it's one of the I guess the quirks of stats models is if you decide to like add new variables and add new things along the way, add constant works well for that.
Okay, cool.
Oh yeah, Sean, you had a question?
Yeah, so is it like these, you said you have to change something 3 or 4 times through your iterations. So
Yeah.
that's like a standard that we're kind of adhere to is.
Yeah. I would say like whether something is like a significant change to your model to count as like a new iteration, it's hard to say exactly what I would count like dropping P values as one iteration, but it does differ from instructor to instructor. Maybe like scaling counts as one. I would say like log transforming also counts as one. Topic 20 has a few other things like creating polynomial features, in like multiplying features together. Those will also count. So the model that you're implementing is the same, just like the variation is really in like your data that you're feeding into it.
Okay.
Yeah, I know that wasn't like a direct answer, but
no,
but I
that's
think
helpful.
you'll see.
Yeah.
All right, cool. Let's talk about some post-modeling things. So the other 2 assumptions that we didn't hit at the start were normality and homoscedasticity of residuals. So that's the thing that I was talking about that some people mix up. The normality is in the normality of residuals. So what are residuals? Residuals are actually your actual values subtracting your predicted variable, your predicted values. So you can get the residuals of your train set by just doing model.resid, and that you get your residuals there. Actually, let me run this first so you can see what this looks like. And there's 2 ways that you can explore this relationship or normality. First, just with a histogram, just based on this data, all right, I can see that it's centered at 0. And there are like some extreme values at like plus minus $200. This is basically like your error put on a histogram. So you can see that it's actually a pretty good sign that we have like a lot of our errors to be centered around 0. The other plot that is often used for looking at the normality of residuals is a QQ plot. And with a QQ plot, ideally what you want to see is all of these blue dots lined up along this red line. I've linked an article talking about how you would interpret these QQ plots. But basically, if you see something like this, it means that your tails are too light to be considered a normal distribution. This is actually pretty uncommon for QQ plot for regression. Typically, what you see is actually QQ plots that look a little bit more like this. They usually go more like this. And that just means that you have heavy-tailed residuals. So instead of my histogram looking like that, you would have a histogram that looks a little bit more like that. What that means is you have more errors on the higher end. Cool. To be honest, like I would, if I was looking at this, I would say, yeah, it makes sense. I would like more residuals to be around 0, but the assumption is that you want it to be normally distributed. So that's something to check for. And really, if you just see a QQ plot like this, it is enough to just interpret the QQ plot. So if you go into this link over here, this is one of many articles online on like how to interpret. You can pretty much see like, okay, if I have something that looks like this, what are the, how would you interpret? So this is light-tailed, and this is a little bit hard to read, but you can see that these like numbers are smaller than like these numbers, for example. So they're not scaled evenly, but that's how you would interpret that. And then, yeah, I also have a histogram here. So I like to look at both. Pretty much most of the time, if you just have a QQ plot, that's fine. I just find that QQ plots by themselves, I always have to look up what the interpretation is, which is why I like to have both there. Cool. So interpretation checks for normality, so that there are light tails in the residuals. The next plot is actually one of my favorite plots. It's technically used for checking for homoscedasticity, which basically means you want even variance in your residuals. But I think that you can get a lot more out of these plots. And these are basically residual plots. So these are residual plots. This is the more common one, the one on the left. And what it's plotting is actually the actual list price versus the error in prediction. And I put a red line across 0 over here because that's what you want to compare it to. So because residuals is actual minus predicted, anything over this red line, you're predicting too low. And anything under this red line, you're predicting too high. And so based on this, you sort of get a sense of how your model is doing across the entire range of the price of your price values. So off the bat, not homoscedastic. Usually if something is homoscedastic, you will see it kind of evenly spread out across the entire range of your actual prices. And that is a sign of consistency in your model. If I have all of my points like scattered around here, they should be also mainly centered around 0, and then like a few maybe here and here. That would be a homoscedastic plot. What I have here with these lines going up, not homoscedastic at all. And what this is showing me too is past a certain value, like let's say above a list price of $800, my model is consistently under predicting price. So that means across the range of price values, my model does not have consistent performance. Maybe here, sure, like between 0 and 200 is doing great. But in this range, there's a lot of over predicting here and a lot of under predicting here. And this is usually something that you can use to say, okay, maybe I might have to cut out the outliers from my target variable. Because past, I would maybe say like $400, my model does not predict well at all. So maybe I should just focus on creating this model to predict on Lego sets that are under $400. So when you see something like this, maybe you can go back and say, all right, as a second iteration, let's refit this on only Legos that have a list price 400 below, and we'll see how it does. Maybe it'll be more homoscedastic that way.
So we could be like, okay, we're going to go back and cut out things over $400. But we're kind of saying, well, it might be harder to predict for over $400, and we might have to do a different model for that, or go back.
Yes.
Okay.
Yeah,
cool.
in real life, and for your project, it's on housing data. So it's actually on like I want to say it's in King County. It's on Seattle housing prices. And there's actually you actually get something that's kind of similar to this. One way to get better assumption graphs is by picking a threshold and say, okay, I'm just going to focus on predicting prices in like a certain range. And for this project, you don't have to create multiple models for different ranges, but you can just outline, okay, I would just repeat this process for houses at like different ranges. Or another approach is you can go back to your business case and say that I'm just going to focus on predicting housing prices for like luxury houses or like the middle range, something like that.
Cool.
Awesome. Anything else? Cool. So I like to kind of see both of these. Oh, and by the way, the blue dots are the train set, the yellow orange dots are the test set. I didn't mention that. I should have put a legend here as well. But yeah, that's what the different colors are. Because sometimes if I have like weird outliers in like my test set, actually I can show you all a quick example. I had it open at some point. I think it is in here. Just bear with me a little bit. I want to say it's in this one. Did I download it by accident? Anyways, so this is not the example I was looking for. But sometimes you have like very different distributions in your train and test set, and that can be obvious if you just color code them differently out here. So here's an example where the data set is not as big, as you can see, but there is one like train test bit where I happen to have like all of my test data at the top here. And that really like skewed my metrics, but that's something that you can add. It's not really a necessity, but I like to see more information versus less. So this plot is one that's very common in like one of the stats models built-in functions actually gives this as one of the 4 plots. But I think this is the most relevant one. So I always have this separate. And this is another one where you actually plot actual versus predicted price. I personally like this one too, just so you can see like what the deviations are in a slightly clearer way. Again, basically actual list price, predicted list price, anything that's over here, we are under predicting because the actual price here was like 1,000, but we predicted like 800. That's an easy way for me to just like, if I forget which direction this one is, I look at this one and confirm. Pretty much show you the same thing. You can see it's pretty much the same thing, just like shifted a little bit. Cool. So with this, how I would interpret not homoscedastic, inconsistent model performance with model under predicting above a list price of $800. If you see like very distinct like shapes in your residual plot, I would mention that as well and use the over or under predicting interpretation to talk about how your model is doing across different ranges of values. And here I'm just guessing, like could be due to the high skew in the target variable. So maybe as like a future iteration, cut out outliers, see how it does. Cool. Any questions before I move on to the last part on coefficient analysis? Nice. All right. So before we talk about that, your final model should not have any variables with p-values over 0.05. Here in this example, I do, but just know that you shouldn't have. You should interpret at least 3 in your final model, and interpretation will differ based on how you scale your data. So if you have no scaling done, so let's start with that one. If I have no scaling done, the interpretation is as so. So a 1 unit change in the variable will lead to a whatever the coefficient amount change in your target variable, this price. So looking at this, let's just take a look at piece count. And the numbers have slightly changed because I reran this, but one additional piece. So if I add 1 piece in my Lego set, will lead to like a 9-cent increase in price. And that is a relationship you can talk about. And you can say that because you have low p-values. If you had high p-values and you're trying to interpret a coefficient with that, that relationship has a relatively higher degree of random, like it occurred due to randomness. So that's why you want to have low p-values always. Same for others. So let's say, what's this? Like star rating. Okay, so play star rating, and the coefficient has changed slightly, but 1 star increase in whatever this is leads to a 9.17 increase in price, a $9.17 increase in price. Here it should be $8.81. You would interpret it the same way for dummy variables too. So these are all my categorical variables. I don't want to scroll through and look for that one specifically, but this is saying that having a Lego set that is aimed for ages 10 through 14 actually leads to a $100 decrease in your price. So here, which ones you choose to interpret, I would say depends on context as well. So maybe depending on your business case, let's say you're trying to see, all right, which features can I talk about that are, that contribute most to the price of a house? Maybe you'll just look through that, see which ones, pique your interest, which ones you think are going to be most relevant for talking to whoever your audience is, base it off of that. So this one's the more straightforward one. If there's scale done, so I did a really, really quick example where I scaled all of my data. And there are also different ways to scale. This is using scikit-learn's pre-processing for scaling. So you can see when I scale my data, all of my numbers are going to be between or in the range of like plus minus 3. So this is all my data scaled. I rerun the model again. And here, you're basically looking at the relative impact of a feature. So again, I'm not sure. I think there shouldn't be any insignificant. Okay, there's like a couple, but when you have them all in an even playing field, and the reason for scaling data is just because something like, let's say piece count, where let's just say Legos have like, I don't know, 0 to 10,000 pieces. So like a 1 unit change in piece count will have a very, very small impact on price. Whereas if you have something like star rating, which is only a 0 to 5 scale, you're going to have a much larger coefficient for these like smaller range variables. So because of that, it's very hard to see the relative impact of your features. So if you want to see the relative impact of your features, that's why you would standardize all of your X features. So from this, all of these coefficients that are spit out, it's a little harder to talk about it in terms of how the like magnitude it impacts price by. But you can actually look at the magnitude of these coefficients and say, okay, well, piece count relatively has the highest impact on price because standardized piece count adds $76 to the price versus any of these dummy variables now have relatively smaller coefficient values, and you interpret them the same way, but usually when you talk about scaled data, it doesn't really add to the contextual, like in context doesn't really mean anything. But similar to this, you can say, all right, features that most positively impact price, you just look at the most positive coefficients. So piece count has 76. What's another like big positive one? I think the one that I had before was like serious play. Okay, that one's at 21. So those are the ones that had the most positive impact on list price, which are the ones that are most negative on the price. The last time I ran this was all the younger ages. You see like very high magnitude negative coefficients. So because of that, you can say, all right, well, if we're looking at all of the features on a level playing field, the ones that have lower prices are the ones that are aimed at, kids or like younger ages. Cool. Any questions on that? I know there's something I wanted to talk about with regards to multiculinarity and P values, but any questions on anything I talked about so far? Cool. I didn't talk about it because it's different from the last time I ran it, but remember we talked about how the different ratings, the 3 rating variables that we had seem to be multicollinear. Now, in this very first regression example that we ran, one of them came up as slightly random. The first time I ran it, I remember like the p-value was much higher. Having a high p-value is a sign of redundancy as well, because they're saying that there's no significant relationship there. Usually, if you have a high p-value, it is one of the indicators of potential multicollinearity as well. And if you're trying to decide, let's say you have like 4 features that are all multicollinear with each other, and you're trying to decide, okay, which of the 3 should I drop? I like to look at the p-values and decide based on that. But that's like a quick note on deciding that. Awesome.
Cool.
Any questions?
So the scaling, that was standard scaling. Is that what you did?
Mm-hmm. That is standard scaling.
That is something that like you do to, is it like almost a check on the results you got the first time to like make sure to compare? Like you said they're like the example you gave about like the piece count versus the rating.
The star rating, right?
The star rating, yeah. Like that's like, one piece count, one increase in piece count versus like one increase in star rating is very different. So then you standardize, but then it's harder to like interpret that for like, well,
exactly.
What is the unit of increase now, right? Is that like the difficulty? Okay.
Exactly.
So, but
exactly.
Yeah.
So when you would use a scalar versus not use a scalar, I think it depends on what you're doing this, or what you want to get out of your coefficients. So let's say that you're trying to do maybe more of an inferential analysis of like house price versus features. And you literally want to find out, all right, out of all the things I can do for my house, what is the most impactful thing I can do? Then maybe you look at your scaled model. But let's say you literally only care about, I want to know like how big I need to make my house to have it hit like a certain price point. Then you would use your unscaled data. And it's actually fine to have several, you can totally make inferences off of multiple models as well. Let's just say like for my final model, I want to use one that has the lowest Rmse or highest R squared. I can pick that. But for some of my conclusions, I can make conclusions based off of some of the prior models as well, that you are not like, you're not constrained by, you have to make all your inferences from this one model.
Okay.
Cool. Anything else? Awesome.
Not right
well,
now.
I know I went through a lot today, so I'm glad I recorded this. I'll put this recording in the Slack channel. The notebook is there for you. If y'all have any questions, you can always feel free to let me know.
Yeah.
All right. Well, it was
so
very
much.
nice. Very nice seeing you all. Let me know if you have any questions, and have a good rest of your day, everybody. Bye.
Thanks.
Bye.
Super helpful. Thank you.
Yes, thank you.